Again, good morning and welcome to chapter 33. We're jumping into optics. We are about to finish this. Basically, we still only have 4 chapters altogether, including this chapter. And there are 2 ideas that need to be explored. The first one is geometric optics, which is covered in chapters 33 and 34. The first chapter deals basically with the laws of reflection and refraction. And the second chapter, I mean chapter 34, deals with the optical devices, basically deals with lenses, with mirrors, and the different types of lenses and mirrors. There are convex, concave, and combination of both of them. And optical devices include, of course, cameras or lenses for cameras for zooming, and also for telescopes and microscopes and things like that that are used in optical correction devices, for example, like glasses that are used and things of this nature. So this is basically the 2 chapters, 33 and 34. Chapter 35 and 36 deals with another type of optics, and that is called wave optics. The difference between the 2, and you will see it clearly, is that wave optics taps into the wave nature of light. In other words, that light is actually a wave. And this relies on an experiment by Mr. Young, where he basically shone light on a very, very small openings, and he noticed the different interference patterns that form. As a matter of fact, you can do this experiment on your own in that, what you do, you can make a small opening, for example, a small hole in a box or something, and shine a light on it, or a cardboard, and shine a light through it. If the opening is wide enough, you will not see much difference. You will see actually a reflection of that opening on the other side, basically, of the screen. So in this case, the image is a sharp image. There is no problem in this case with geometric optics. All you have to think of as that light as being just a beam of straight, whatever it is. It doesn't matter what its nature is. It could be particles for all we care for. And those particles are shouting through, going through the opening and going from the other side, producing an image replica of the opening that you made. Doesn't matter. You make it spherical, you're going to get a sphere. You make it square, you're going to get square. You make it into a, I don't know, any kind of shape, you're going to have an exact replica from the other side. However, when the opening has become smaller and smaller and smaller, then you will see that the light starts to diffuse. In other words, the image is not as sharp as it used to be. On the edges of the shadow, and the edges of the image, there will be a little bit of spread of the intensity from high intensity to low intensity. And that is an indication that light is actually, on small scale, is actually a wave. So this is basically the idea behind it. People struggled with this point. What is the nature of light? I know some of you in this class are sitting in physics 4B, and chapter 32 is immediately before chapter 33. Chapter 32 deals with actually electromagnetic waves. That light is actually an EM wave, an electromagnetic wave. So let's put it in a historical context so that you understand what's going on. Before Newton, there were people like Huygens who did experiments on light. And actually before Huygens, there were the Greeks also who experimented with light. And this is probably one of the only recorded experiment that Greeks have done is on the law of refraction. So the idea was this, that whatever is in light, we can assume it's some sort of a particle like a tennis ball, for example. When it hits the ground, it bounces off, and that is the law of reflection. When it goes through a medium of different properties, different index of refraction, basically, it refracts, okay? So those are the 2 phenomena that were known. Mr. Newton put it together and came up with the so-called corpuscular nature of light, that it's made up of tiny particles, okay? That idea held for a long time until later on, because of what I was describing earlier in terms of openings and things like that being made small, is that Mr. Young actually conducted an extensive experiment, a series of expensive experiments to show that actually light is a wave and exhibits wave patterns, wave interference. So now we had to abandon that idea that light is actually a particle, but rather it's a wave. This is around the beginning of the 19th century, around 18 something, okay? Meanwhile, people were still working on electricity and magnetism, and toward the end of the 1800s, basically, around 1876, is when Mr. Maxwell came up with, he put together all of these laws of electricity and magnetism in a set of equations. And when he solved it, he found that actually light, and this is what inspires from chapter 32 of this book, is actually an electromagnetic wave. So not only Mr. Young was right, that it's a wave, but Mr. Maxwell found exactly what was waving, namely the electric field and the magnetic field, where what is going up and down and moving and things like that. So this is basically it seems like it sealed the fate of the corpuscular theory that Mr. Newton came up with. This was great. Up for at least almost 10 years after that, there was another phenomenon involving light that people couldn't understand. And that is when you shine light on a certain on metals like nickel, for example, and copper and those metals. If light has the right frequency, electrons are ejected from it. This is the photoelectric effect. This is what you see on houses, on the roofs of a lot of people. Sometimes they use it actually for generation of electricity. So the photoelectric effect was a phenomenon that really you cannot explain it with a wave. Why? Because you need a specific frequency for it to happen. Just before the work of Mr. Einstein, there was a work of Mr. Max Planck in order to explain another phenomenon also involving light trapped in a box, the so-called black body radiation. He introduced the constant, and that constant, he apologized for introducing it because it made no sense to him physically, but it explained beautifully the black body radiation. And Mr. Einstein borrowed that idea of Mr. Planck and said, you know what? Light is actually not a wave anymore. Light is actually a particle. So what's going on? The particles of light, he called them photons. They hit the electrons of the metal, and if they have the right frequency, then they will eject an electron, each and every one of them. So now, it seems like we went a full circle. We went from corpuscular nature of light to a wave nature of light, so especially in the case that something is waving, to a confirmed wave nature of light, namely chapter 32, because the electric field and magnetic field, back into the corpuscular nature of light, back into being its photons. So the modern basically perspective of light is that light is actually both, depending on the experiment. If you're doing a photoelectric effect, then in this case, light is actually a particle. If, on the other hand, you're doing, for example, interference, like for example during a Young experiment, light is actually behaves as a wave. So light can be a wave. I mean, behaves like a wave, and light behaves like a particle in the same time. So this is the so-called duality nature of light. Light is both. So this is basically a big introduction to everything else. Okay, so this entire 4 chapters that are coming. In terms of content, we really don't have a lot of stuff left. I know we still have a lot of time, so we're going to finish with this course in plenty of time. So depending on how you guys feel about it, we may dig deep into some of these ideas. So we may introduce some higher stuff, and if you guys are up to it and you like, we can do it. And if you guys don't think that it is something that we probably don't need to explore further, it's fine. We can do more applications and things like that. So that's in a nutshell what I'm trying to say here. That is one thing. The other thing also, the lab this afternoon is going to be, we're not going to be doing it this afternoon. We're going to do it next Monday because we already did the reflection and refraction a long time ago when we did waves, and it's part of the overall wave nature, not just for light. So instead of repeating that lab, we're going to combine the ideas of reflection and refraction with the index of refraction, the next lab on Monday of next week. So there will be no lab today, but there will be a lab next week, borrowing some of the ideas from the previous lab that we did and adding to it the index of refraction. So in other words, we will have one less lab than what we have originally planned, because we already did it as part of a big lab way back when we were doing waves, when we were doing chapter 15. Does this make sense to you guys? At least the ones who are here?
Yeah.
Okay, very good. So let's delve into today's chapter, see what's going on with it. Let me share with you the screen. Share. I don't want the screen, I want just this slide. Okay, so the idea, first of all, with light is its speed, the speed of light. There was a confusion leading to the work of Mr. Alhazen whether or not light was traveling with a finite speed or an infinite speed. Is light infinite speed or finite speed? He argued that it cannot be infinite speed, because if it's an infinite speed, and this argument actually was laying around in a lot of literature before him, and he actually put it together, is that, look, light comes from very far away stars. Okay, and if stars are spread uniformly throughout the universe, we must, if it's infinite speed, all of these dots, they should be sending light all the time. So there should be no difference between day and night. It should be always lit, basically, whether the sun is there or not. So that's basically his argument based on the distance of the stars. And the stars, he argued, they must be very far, because we cannot really, I mean, it's very hard to measure the speed because it's probably super fast, but it definitely is a finite speed. Mr. Galileo tried to actually conduct an experiment to find that speed. So what he did was he got one of his people who works with him, one of his colleagues, to carry with him a lantern. So, and he told him, go to the other side, about a mile away, go to the other side of the mountain, and I'm going to light the candle, what should we call it, the lantern, okay? I'm going to light it, and when you see me, when you see the light, light yours, okay? So, and Mr. Galileo was supposed to measure the time for the light to travel from him to the other guy about a mile away and come back to him. So now he knows the distance, let's say about two miles. If he can measure the time, all he has to do is just divide the distance, which is roughly about 2 miles, divided by the time it takes for light to travel, okay? Since he didn't have a clock or a watch or anything like that, he used his pulse, okay, to measure the time. And he collected a lot of data, okay? He noticed one thing is odd about this data is that it fluctuates a lot, this data. So he said, okay, let's redo the experiment in a different fashion. And what is it? He said, we're going to sit next to one another. You and I next to one another, okay? You don't have to go to a mile away, just here in the same place. I'm going to light the lantern. Don't light yours until you see the light, okay? So the other guy is waiting, watching for the light of Mr. Galileo. So Mr. Galileo lights his light, put his hand on his wrist, try to measure the time, and collect the data. Again, the distance now practically is 0. He wanted to see the difference between the times, whether or not the times were making a difference or whether or not. Okay, and he saw very little difference. So he concluded that This experiment did not measure the speed of light. So basically, it failed to measure the speed of light. Why? So what did it accomplish? He said that it measured the reaction time. That's all. Because that's true. I mean, if both data are the same thing, because when you are very close from me, all I'm measuring is how long it takes for you to react and how long it takes for me to react. So that's all. Since we really don't have any distance, light is basically traveling nowhere at this point. So all he was measuring is the reaction time for both of them. And that's why this experiment, it was abandoned, and at the end, basically, it failed to measure the speed of light. See how people think? I mean, I really want you guys to be in the mindset of scientists and people who try to come up with cheap things in what they do. It was a little later when Mr. I think about 50, 60 years later, when Mr. Kramer came up with actually a better, or was it? No, I forgot the name, okay? I think I may have probably confused him with somebody else. Anyway, the experiment is the following. He looked at Io, which was already discovered by, among other, discovered by Galileo, one of the moons of Jupiter. So Io goes around Jupiter very fast, in about 42 hours or so, okay? Around Jupiter. So here is the Earth, here is Jupiter, okay? And here is the Sun, okay? So if I measure the time for Io to go one whole cycle around Jupiter, okay, today, and wait, so light is traveling this whole distance for me to observe Io. And wait 6 months later, when the Earth is on this side. By the way, Jupiter takes a long time to move around the Sun, okay, compared to the Earth, because the Earth is much, much closer. So the Earth is probably much closer. It's 1 astronomical unit, whereas this one is about 5 times as much, okay? So the Jupiter takes a long time to go around the Sun. So if I wait 6 months later, I would redo the experiment. Light now is basically traveling this extra distance, which is twice the astronomical unit, or 300 million kilometers. 1 astronomical unit, this distance is 150 million kilometers. Okay, so that extra distance will account for a shift in the period of Io. And when he looked at the data and the shift and found the difference between that shift and compared it to this distance traveled, now you have a difference in time. So now between the frequency and this frequency, or the period and this the period and the 6 months earlier. So now he was able to find an estimate of about 200,000 kilometers per second for the speed of light. So now for the first time, using astronomy, we had actually a closer number, which was actually close enough. I mean, it's the actual number today is 300,000 or 299,970 something kilometers per second. Okay, practically we use 300,000. It was later when Fizeau, a French experimentalist, came up with a better measurements for the speed of light. And that involved a synchronized, basically, gear with the source of light. So if you turn the wheel, especially fast enough, and it has gears, it has actually openings in here, and if you send it fast enough so that the light hits a reflector, and when it comes back, the gear will just move one distance from there. Since you know the distance between the reflector, the distance traveled back and forth, and you know how fast this one is spinning, you can find the time, just the inverse of the frequency of this fast spinning gear, versus the distance traveled, and now we have a better estimate. This experiment was refined further and further, and now we have a better value for the speed of light, which is, we're going to take it in this class 3 times 10 to the power 8 meters per second. So this is the value, the operating value that we're going to be using. Unless we're doing atomic physics, this is a number Let me move the screen out of the way. Yeah, unless we're doing atomic physics, we're going to use this number, where the numbers, the precision is going to be extremely high for those experiments. This is a number that is close enough. Otherwise, 2.997 something that we can use for the speed of light times 10 to the power 8 meters per second, okay? Or 300,000 kilometers per second, or 300 million. This is 300 million meters per second, or 300,000 kilometers per second. So light, now we know its speed. This is in vacuum. Or air, okay? Inside any medium, though, light goes through different process. Inside water, for example, light doesn't travel as fast. I mean, look, what's happening inside a medium is you have two atoms, for example, sitting one next to one another. Light hits this atom, excites the atom. During that time, light is traveling nowhere. Then the atom goes excited, and for it to go back to its ground state, it's going to emit the same frequency that it hit it. So now, when it goes back into the ground state, this light, then it travels with the speed of light between the two atoms until it hits the next atom. It's basically, during that time, it's absorbed, then re-emitted again and again and again. Light appears to be traveling with less than the speed of light in a medium, in any medium, including air, by the way, whose index of refraction. And when we do the experiment on Monday of next week, I want you guys to choose a number other than exactly 1 for the index of refraction. I'm going to define the index of refraction very shortly. Because even in the air, there are molecules, albeit very far apart, that you don't see any change whatsoever in the speed of light. But in the case of water, for example, the molecules are very close from one another, and they disrupt, at least because they're absorbed. They absorb light for a short moment. That moment amounts to an extended time during which light is sitting in that material before it's transmitted. There are 2 types of materials where light is completely absorbed, and those are opaque materials. There are transparent materials like glass and water, where light is actually absorbed momentarily and then is transmitted in the other one. What we're talking about in here, what we mean by light, is visible light. What is transparent for visible light, like the glass, for example, which is transparent for visible light, is not true, for example, for the infrared light. Infrared light, glass is actually opaque. When infrared light, for example, hits the glass, it does not leave it. It stays trapped in it. Hence, for example, if you look through your microwave that has a mirror, that has a glass in there so that you can see what you're cooking, there is no infrared light coming out of it. It's trapped inside that oven, basically in that microwave, to cook the food. And as a matter of fact, this is actually the essence of the greenhouse effect that is used for example, in structures. They use plastic that has the same properties, and plastic is transparent when it comes to visible light, namely light will come in and go through it, but then it heats up the plants and the soil inside those greenhouses, and those ones, their temperature, basically because now they take the material, they take the infrared, they take the visible light, they absorb it, but they emit it in the infrared range. When the infrared rays try to leave the glass, it does not, or tries to leave the plastic, it does not. It's reflected back into it. So in this case, the material is not transparent for those frequencies. So again, what I was describing earlier for the speed of light has to do with the visible light. And that was a distinction that was not known until chapter 32, until Maxwell's equations, because we thought that light is visible light. And then when Maxwell solved his equations, he found that actually light has a huge spectrum, and visible is just a very narrow region of it. So the visible light ranges anywhere between 350, about 400 nanometers in wavelength, to about 700 nanometers in wavelength. And anything that has a higher frequency in here, or lower frequency on this side, I mean, shorter wavelength in here. So this is the blue light, or the violet light, actually. And this is the red light. And anywhere in between them, the green, the yellow, and all of the other colors, they're actually in here. So this is the visible region. In this region, you have the UV region, you have the X-ray region, and you have even far more damaging and more energetic waves, and they are the gamma rays, okay? And on this side, you have the infrared region, and you have also the microwave region, like your cell phone and things like that. And then you have the radio region, and actually you can have, this does not end on either side, okay? The wavelength does not end on either side of the frequency. This is longer wavelength. This is higher frequency. Which means energy, more energy. So this is the spectrum. This is the EM spectrum. This stuff is supposed to be covered in chapter 32. And because some of you are not taking chapter 32, this is basically a refresher so that you guys see what's going on, okay? From chapter 32, we know also that the electric field and the magnetic field are the ones that are waving. So the electric field is actually a wave. In the harmonic sense, this will be some intensity in some direction times some cosine of a frequency and wavelength, okay? And the frequency is given by, or let's do the wavelength first, is R, okay, times the direction in here of the wave, divided by, okay, let me not use this. Let me take it in the polarized, in the, I mean, moving in a specific direction. Let's say, for example, the x direction over lambda minus 2 pi times t over period t, okay? This is basically what you guys, similar to the problem that you guys had in the exam. The magnetic field is in another direction with an intensity B naught times the cosine of the same 2 pi x over lambda minus 2 pi t over t, where t is the period, related to the frequency in such a way that t is equal to 1 over f, and lambda is the wavelength, and lambda is related to the wave number as being, what is it, 2 pi over k, okay? And that is the wave number, and we have everything in here. So this is the stuff that you should have seen in physics in chapter 32. You will also note that both the electric field and the magnetic field are perpendicular to one another, and they are perpendicular to the direction of propagation, which is in the x-axis, meaning both the electric field and the magnetic field cannot be in the x-axis, meaning bx is equal to 0 and ex is equal to 0. This is one of the results of coming from chapter 32 again, okay? So this is the stuff that you have seen. I mean, normally the wave can travel in any direction, but I took it arbitrary in the x direction so that I write this expression easily. I don't have to do a dot product in here or anything like that, okay? So this is similar to the problem that you guys had in exam for waves from chapter 15. So it's basically all of this stuff that we have in there. So this is in a nutshell what we know up to that point for the speed of light, okay? So that's, I mean, for light in general, and light that we talk about usually in the context that we're talking about is the visible light. And at least in this 4 chapters, but don't lose sight of the fact that light in general is part of a huge spectrum. And that is the fact that it is the electromagnetic spectrum. And the electromagnetic spectrum spans all of the frequencies that we know we use, for example, for telecommunications on this range. Actually, we can use also radio waves for telecommunications, and we can even have extremely high frequencies. The visible light is between 400 nanometer in wavelength and 700 nanometers in wavelength. Okay, give and take few. Okay, so if you see a wavelength that is slightly more, don't be afraid don't be too scared with it. So this is in a nutshell review from chapter 32. Okay, and the reason why I'm doing that again is because of the fact that physics 4C does not necessarily touch upon chapter 32. Some of you, as I said before, are sitting in for physics 4B, whether with me or not, and you will know this stuff when it comes to chapter 32, and we're slowly getting into it in there, at least with these classes that I'm doing, okay? So This is basically in a nutshell where we were. So now let me go back into the materials. Inside that material, light travels with an apparent speed that is by definition c over n, where n is the index of refraction. C is the speed of light that I mentioned before. C is the 300,000 kilometers per second or 300 million meters per second. Okay, so V now, because n has to be more than 1. N has to be more than or equal to 1. For air, n is equal to 1 for air or vacuum. Okay, anything else, n is more than 1. That means that the speed of light is usually in a given medium is less than 1. Okay, I mean less than the speed of light. So the speed of light in vacuum, which is the number that I mentioned before, which is this number, is the highest speed you can have for light anywhere. After that, in any given medium, it's given by this expression, okay, where n is the index of refraction. So, experimentally, observation. It was shown that if I have a material in here, let's say, for example, a mirror, okay, that separates two regions of space. One of them is the air, and the other one is a completely, basically, a reflecting material, like, for example, silver, okay? Very shiny, smooth surface in there, okay? So what happened in this case, if I have an incident beam of light, let me, yeah, and then it hits the material in here, it's going to reflect in such a way, if this is the normal, so this is the normal to the surface, this is what I'm going to call the incidence. This is the angle of incidence, theta A. This is the angle of reflection, theta R. So this is the reflection. Experiment has shown that these two angles are the same. Theta A is equal to theta R. Okay, so this is easy enough. This is geometry, okay? It has nothing to do with anything else. The only thing is, you have to remember is that the angle is measured within the normal, by definition, from the normal. Okay, so this is law number 1. Okay, the second law now involves the separation between two different media, one of them with different index of refraction than the other. So again, let's take that in general case. So let's call this one law number 1. Law number 2 now, or law of reflection, that you can call it that way too, is that you have a medium with an index of refraction in A and a medium with an index of refraction in B, and this medium is of a different type. Let's say, for example, it's water, okay? Then in this case, you have, again, I'm going to define the normal in here, and I'm going to take, this is the incidence again, theta A. Well, theta B is given this way. So again, this is the refracted. So again, this is the incident, and this is refracted. Refracted. Okay. Well, we're going to prove this stuff, by the way. The second law says the following, that NA sine of theta A is equal to NB sine of theta B. So this is law number 2. Okay. Both laws, actually, the second law usually is referred to as Snell's law. So when you see in the book problems and they tell you to refer to Snell's law, this is what they mean, okay? And sometimes this is actually called the second law of Snell, and the first one is actually the first law of Snell. But it was that they were discovered way before, okay, at least by the Greeks. I mean, as early documented as past by the Greeks. So this is not really a new observation. So these are all old ones, okay? So these are the laws of Snell. Toward the end of this chapter, and I hate that a lot, I'll express my opinions about it at this point in here, is that they introduce Huygens Principle, okay, to prove these two laws. And Huygens Principle taps into the wave nature of light. Basically, it says that I mean, if you think of a wave front of a wave moving from point to point, the way you can imagine that is that every single point on the wave front becomes a source for a wavelet. So every single point, you're going to take it and you're going to see how the wavefront will behave in front of it. You take that point and make it a source. So this becomes a source, this becomes source, every single point. And between 2 points, of course, you know that there is another point. So this number of points is an infinite number. But for illustration purposes, you take just equally spaced points. And then you draw a new source coming from there, a new wave coming from there. And you draw another one coming from the second one, and you draw another one coming from the third one, and so on and so forth. So once you take all of these points and you draw the waves coming from them after a certain amount, of course, of time, so that you reach the new points, now the envelope of all of these waves that are formed by these wavelets emanating from these points sources becomes the new wavefront. So this is the principle of Huygens, and we use that to prove these two laws. However, the whole chapter title is called Geometric Optics. And geometric optics should not tap into the wave nature of light at all. That's why I included there, following the treatment that Feynman had and some other textbooks actually, the principle of Fermat. The principle of Fermat uses a different idea. It says the following, and with that, what we're going to use, because we're going to stick to the spirit of this two chapters, namely that light is not a wave, that light is a particles. We're going to use that to prove these two laws, okay? So what Fermat principle is saying is, in going from point A to B, this is point A, and this is point B, okay? Light takes the least time. We're going to show if it has to hit this mirror, this is the least time in such a way that the angle of incidence is equal to the angle of reflection. And we're also going to use the principle of Fermat, saying that if light has to travel between point A and point B again, by refracting through this medium, it will do so in such a way the time it takes going from A to B is given by this expression using the least time. So I'm going to use the least time, and I added it as one of the things in the discussion, in the notes for the chapter, to show that these two laws work, that these two laws are true, okay? Obviously, what is the deal with the principle? Principle is something like a postulate you're going to put together to prove some observations like this too. So if it leads to that, that means you hold the principle to those only experimental observations. So it becomes like a law itself, okay? So that is basically what the idea behind the principle. So Huygens came up with that principle. Is it true that every single point on a wavefront, first of all, you cannot define every single point, okay? There is a mathematical basically defiance in that, and that's a way that you cannot really do it. But again, you can use an approximation, okay? That every neighboring points, you can just take whenever you're satisfied, okay, this is close enough, so I'm good. So I'm going to draw the sources, the waves coming from them, and then at the end, I'm going to take the envelope of that waves, and that becomes a new wavefront, and that works, and that is true. That principle could prove these things. But I'm trying to avoid using it for the reason that I want to stick to the idea that we don't need waves to do geometrical optics. Geometric optics can survive on its own without the need of the wave nature of light. So this is the whole point that I'm trying to make in here. So we're going to prove these two relationships. Okay. And there is actually another digression even in the chapter. I was looking at it in this morning and I was kind of a little bit annoyed with it, but I'm going to mention it anyway in here. And that is the fact that light itself is actually the direction of the electric field is the polarization of light itself. Light is polarized. I mean that is a fact that you can experiment with in the evening. For example, light comes from every single direction. All you have to do is just take one of those polarizing glasses and put it on, and then all of a sudden the image becomes a lot better because those glasses, they will cancel all of the other lights and give you just one direction, and that way you will have a better view of what is in front of you in the evening when you're driving especially. So light has preferred direction, and the preferred direction is that of the electric field, because the electric field comes into your eye and interacts with the retina of your eye and basically excites those atoms. So if it has all the directions everywhere, you will have a fuzzy picture of what's in front of you. But if you have it polarized in a specific direction, then the electrons inside your retina start to move only in that direction and gives you a preferred direction in that. So that is why polarization in here is important. Now, if you take a polarized light this way, so you run it through a polarizer, this direction, so that light has every single direction, every which way, but now all of a sudden when it emerges from a polarizer, it has this specific direction. And if you run it through a second polarizer that is making a 90-degree angle with it, it's going to cancel this polarization, and you're going to have no transmission whatsoever on the other side. So if you take two polarizers and you put them one next to one another, yes, you're going to have the same light transmitted, but if you start to tilt it, the intensity starts to drop up until it cancels completely. So that's the idea behind the polarization. It has to do with the direction of the electric field. Polarization has a lot of applications and basically rules. The key thing in here, it has to do with the direction of the electric field and not the magnetic field, because when you take chapter 32 again, you will see that this B naught, the intensity of the magnetic field, is that of the electric field divided by C, and C is 300 million meters per second. So the intensity of the magnetic field is so small compared to the intensity of the electric field, and that's why we were equipped to respond to the electric field more so than the magnetic field, although both of them are present in light. By definition, polarization has to do with the direction of the electric field. So light is polarized. Along the direction of the E field, the electric field. Again, technically, I really don't like this much because again, we're tapping into the electric nature, the wave nature of light, okay? But because this chapter, you will have problems to deal with it and things like that, so we really have to introduce this idea of the polarization. So again, if you run light through a polarizer, so imagine with me that I have a polarizer in this direction, and I have light that is coming in every which way. Okay, so this is the electric field, by the way. Okay, and every electric field in here is perpendicular to its own magnetic field. Remember that what I said from chapter 32 again, that you didn't take for a lot of you, is that the electric field and the magnetic field are always perpendicular to one another. Okay, so forget about the magnetic field for polarization. Just focus on the electric field only. Okay, so light is going to go through this polarizer. So this one will block every single direction with the exception of this direction. So when it emerges from this one polarizer, so it's traveling through this material in here. So when it emerges, you will only have, this is the direction of the electric field that is going to survive. So now it's polarized. So this is unpolarized. Basically, all directions are along. This is typical of light. Light, for example, from incandescent light is really unpolarized because the electrons inside the material there move in every which way direction due to thermal agitation, and then during that motion they emit electricity, electric fields, and magnetic fields, and the electric field will take every direction that the electrons are moving. So light comes out completely unpolarized. However, for an antenna, dipolar antenna, light is actually polarized because the electrons will move along through the antenna up and down, and when they do, they emit light. So light that is going to emit with them, is going to emerge from them, will be polarized because of the preferred direction of the electron. So light from an antenna, like for example telecommunications, usually is polarized. Okay, so that is, unless they go through different reflections or things like that, in which case they lose that polarization, in case they become random again. Okay, so now light becomes polarized. If you take another, so this is a polarizer. If you take another polarizer and put it in another direction, okay? So remember, the direction that is coming in here has this preferred direction, and you take it and make an angle with the previous one, an angle phi. Phi. Then in this case, this light will only pick up the cosine phi of it. So E will be, that is going to emerge from the other side, will be on this direction only. So this is the direction of light. So this is the component along this direction, and that is going to be E naught. So I'm going to call this one E naught, by the way. E naught times cosine of phi. Cosine of phi because we're doing the adjacent. So if you look at it this way, this is the direction of the electric field that that initially came up from the first polarizer. This second polarizer is called an analyzer, actually. So you're picking up just this component where this angle is phi. So obviously, using the trig in here, too big. The trig identity in here, this is the adjacent to that, this is the hypotenuse. So this one is just cosine of phi times this one. Okay. Again, from chapter 32, we will define the intensity of light, and we will see that the intensity of light is proportional to the square of the electric field. Actually, it's going to be proportional to the square of the electric field plus the magnetic field. But because of this relationship, we're going to cancel one of them, and we express in terms of the electric field. Okay. So again, this is an anticipation for those sitting in physics 32, physics B, okay, 4B, and from chapter 32, okay. And if you're going to take it in the future, again, you will see this chapter basically where you find the intensity. So this is the intensity. The intensity will be expressed as the square of either one of them, either the electric field or the magnetic field. As a matter of fact, there is another expression for the intensity that involves something called Poynting vector. Okay, and that Poynting vector is actually the product of the two quantities, which you can actually use to eliminate one of them, and it's still proportional to the square of the electric field. Since the focus of polarization is all along the electric field, we're going to express it in terms of the electric field. So the intensity that is going to emerge from here is going to be this intensity, the original intensity before you run it through the analyzer. This is I naught. This I naught is proportional to E naught squared. But this I that is going to emerge from here is proportional to whatever those coefficients in front, which is epsilon naught and all of the permittivity and permeability, times E naught squared, which will give me I naught times again cosine squared. So the point in here is the intensity in this case would be proportional to this intensity times cosine squared of phi. This is called Malus's law. Actually, it was an experimental law. But now the proof for it, if you wish, you can go back to chapter 32 and prove it with a little bit of work, and you can prove it and show that it's true, okay? Okay. The reason why I'm again mentioning this in here in this context, because you're going to have it as part of the homework problems and part of the discussion problems and things like that. And it relies, so the proof for it, if you wish to prove it, you really have to delve in chapter 32, since chapter 32 is not part of the requirement for this class. Basically just take it as a law, which was actually an experimental law. That's how we found it, okay? But the proof for it is not really hard to do if you can go back to chapter 32. Does this make sense to you guys? So they will give you the direction between the analyzer and the polarizer, and that will be the angle phi. Square the cosine and multiply it by whatever intensity or the new intensity, and that's how you find it. As a matter of fact, as I was describing earlier, if phi is equal to 90 degrees, cosine of 90 degrees is 0. So if I take the analyzer, so think of it as this, the second one is your analyzer. So if the phi is 0, then cosine of 0 is 1. So when you square it is 1, so the intensity is exactly the same. As you start to move more and more, then the cosine of phi is increasing, and this cosine squared in here starts to become less and less when you square it until it vanishes completely at 90 degrees. Okay? Then in this case, as you run light through a first polarizer and a second polarizer, and in that case, you will have no light coming from the other side, 0 intensity. Make sense? Yes, no, maybe? What do you guys think? Does this expression make sense to you? Or should I repeat it? Okay, very good. When you guys do that, I really don't see the chat, so sometimes you guys are writing and I can't tell. Okay, so hopefully you guys are on board with this one. There is another thing that has to do with the polarization, and that's a little bit at least kind of, because again, we didn't really do a chapter 32, but again, light, let's say for example, light is coming through a medium. I don't forget, I'm not forgetting the fact that we need to prove those two laws using Fermat's principle, okay? So when you have light, so you have a reflected material, you have a material in here. So actually part of the light that is incident in here, so this is your angle theta A, is actually reflected even on, so there is an index of, I'm going to take it air in this case, okay? I'm going to take 1, which is typical problem actually. And this one is a medium n, which you can think of it as a glass, where n is equal to 1.5 for glass, or 1.33 for water. Okay, so that's our typical examples that we usually have. So again, there is the angle of reflection, theta r, and so this is the incident, this is the reflected, and this is the refracted. The refracted usually is less than, so this is theta b, okay? Theta A and theta B are given by that relationship. Because n, I took it to be 1, so it's going to be sine of theta A is equal to n times sine of theta B, okay? Theta B, okay? In this case, you will always have a theta R, okay? And part of the lab that we'll be doing on Monday, next Monday, is the fact that we will be measuring the intensity, okay? You will see that as n starts to increase, the refracted in here will start to change, will be less and less, and in this case, it's going to increase the reflection. So there is a reflection and there is a refraction. So this is the reflected, and this is refracted. Okay. One condition, okay, for the refraction is the total reflection. If I go back into this expression, okay, and assume for a moment that NB is more than NA. Okay, and look at this expression. When am I going to have theta A equals to 90 degrees? I'm sorry. Yeah, theta A equals to 90 degrees. In other words, the refracted light is equal to 90 degrees. So theta A, or the incident light, is theta A is equal to 90 degrees. So if I plug in the expression in here, I will have NA, or is it, did I have it wrong? Yeah, sine of theta B in this case will be equal to NA over NB, because sine of 90 degrees is 1. So there will be a point in here where the angle of incidence cannot be any higher than this value, cannot be higher than, of course, this value. This is the one. It's always from the normal. And that is given by this expression. So this is the critical refraction. After that, there will be no more refraction. Okay. This angle can approach this 90 degrees. After that, that's it. It's gone. Okay. So you can vary it, and actually in the experiment, you will vary the angle theta until you reach almost 90 degrees. You will see this angle. Then after that, there will be no more refraction. It's going to all 100% is going to be refracted, of course. Okay, skim the surface. So to continue with this point in here, the light that is coming in here can be polarized because it's traveling on this direction. And I was mentioning the fact from chapter 32, you can have polarization. Light can be polarized in any direction other than this direction, other than the direction of travel. So think of it as, if this is the direction of travel, light can be in any of these directions, okay? The electric field can be in any of these directions. So I'm representing it by these arrows in here. And any of this actually is good enough. The only thing is, I don't want you guys think that there is a direction in this direction. So if it's going this way, if light is traveling this way, this is all of it is possible, but not in this direction. The electric field cannot exist in the direction of the propagation, and no is the magnetic field either. So both of them are perpendicular to the direction of travel. So if it's going this way, so light can be polarized in whichever direction, but not in the direction of propagation. Okay. So now here is the trick. Okay. And this is due to Mr. Brewster, who was working on this experiment. Light has two components when it hits the surface, basically. A component that is going up and down to the surface, and a component that is perpendicular, parallel to the surface in here. Okay. So in this point in here, light that is parallel will emerge from this side, basically. Actually, different representation with this one will be like this. Actually, let me redraw it this way. So light can be here, or it can have a component that is going into the screen. So the component that is going to screen is going to be parallel to this surface separation between them. And that is going to be the main one that is going to be emerging from it. Occasionally, depending on this angle theta A, I will have the other component. But overall, I should have mainly this direction. So yes, you will have, so instead of having so many lights that came in with this direction, they're all of them, both of them, actually in all directions possible, okay? Okay. Now, all of a sudden, you will only have mainly in the direction parallel to the surface, actually, okay? On the side of the surface for the reflected ones. You ask what happened to the refracted ones? Refracted ones will have the difference, okay? Because if this one was transmitted, so it's going to be here, here, and this one probably is going to be here, and then in here. Okay, so it's the opposite in here. So this one can be used then. Actually, usually it's random. I'm sorry. Usually it's both of them. We don't care about this one much, honestly. We care only about the refracted, because the refracted will be reflected. I'm sorry, will be mainly polarized. Okay. Mr. Brewster kept on changing the angle theta A, and he noticed that there is an angle that matches the polarization. That is called the polarization angle, when actually none of the other components emerge. Only these components emerge. So at a certain angle, theta, he called it theta P. So this is theta P. This angle, of course, will change. All of the light that is going to be emerging is going to be polarized. So this is 100% polarization. Okay. Of course, in this case, the angle theta, this one will have all kinds of random stuff that we don't care for it. Okay. At this point, we care only about this one. But the theta P, of course, will be equal to theta P in here. This angle in here also is 90 degrees. So Brewster's observations again is that at theta P, at this angle, the reflected light is polarized. I mean, when I say that, is 100% polarized, because the other one is partially polarized at any other angle other than theta P. Obviously, when he increased also the angle, it became also partially polarized. So that's not useful. So there is an angle with which this becomes extreme and this becomes useful. Okay. So again, the angle between the theta P and the theta, so let me redraw this one, it became a mess in there. So let me redraw it clearly for theta P, the condition of polarization. I'm sorry, that is not an axis, that is just normal. So again, this is the ideal angle theta P. The law of reflection and refraction required that this theta P, this is also theta P, okay? Well, this is theta B, always, okay? This is the refracted. So I'm going to take the index of refraction in here, and I'm going to take it 1 in here. Again, you can take it NA and NB if you like, okay? So if you want to, we can take it NA and NB, just to not avoid that. So this angle is 90 degrees. So basically from the get-go, we know that this angle and that angle also add up to 90 degrees. That means theta B plus theta P is equal to 90 degrees also, because this add up to 180 degrees and this is plus that, then must be the other 90 degrees that is missing from here, okay? So if we apply Snell's law, we know that N, oh, let's use that. N sine of theta P must be equal to NB sine of theta B. But I know from this expression that theta B is equal to actually 90 minus theta B, theta P. So theta B is equal to 90 degrees minus theta P. So I'm going to place that in here, and we're going to have NA sine of theta P is equal to NB sine of 90 degrees minus theta P. Okay. And if you remember from your trig identities, this is actually a cosine of theta P. Okay, this is a trig. So all I have to do is define by the cos, and now I have the tangent. So the tangent of theta P is equal to NB over NA. In my example, the original one with n equals to 1, NA equals to 1. So this is divided by that, and this is equal to n. Okay. So this is Brewster's expression now. So this is Brewster's law. You will need this one also. Brewster's law is expressed in general like this. But for simplification, sometimes you have it written like this one, where the index of refraction is just the index of the, I mean, we take air or vacuum from the top medium, okay? So this is basically how you're going to connect these two together. So this is everything in terms of what we need for homework problems and everything else. So the chapter is done. We still have about half an hour. Let me finish let me prove those two laws for Snell, and then we're going to be done with it, okay? So the first law, the law of reflection. Here is the challenge. I'm going to take point A as a starting point, and point B is somewhere in here. It doesn't have to have the same height, by the way, here, okay? And I want to find, going through this reflector, what is the condition that I need to have? Obviously, I have two options. I could go straight in here and go here, meaning I cut through straight in here. This is the shortest distance. If I have to travel to the mirror, I can go straight to it and then travel to point B. Or I can go here just below point B and then go to point A. My point in here is that actually there is a condition with which this is going to happen, where the distance AB going through this point C will have the shortest time, or the least time. Not the shortest, the least time, okay? And that will be in such a way that this is the angle of incidence theta A, and this is the angle of reflection theta R, in such a way that theta A is equal to theta R. So let's prove that, okay? Obviously, I need to find this distance, and I add to it this distance, and take its derivative, and require that the derivative is 0. That is basically how we find minimum or maximum of any function. So what I'm going to do in here, I'm going to take this point in here, 0, my starting point, this point x. I'm going to call this whole distance d. This distance, I'm going to call it a, and this distance, I'm going to call it b. It's clear from the geometry in here that the distance from a to c is just the square root of a squared plus x squared. So the distance AC is simply equal to the square root of a squared plus x squared. That's simple enough, okay? The distance from C to B, CB, is again equal to b squared under the square root plus this one squared, and this one is d minus c squared, d minus x squared, because I took the distance between, the horizontal distance between the points A and B as being just d. So it's going to be equal to square root of b squared plus d minus x, the whole thing squared, okay? What I'm saying in here is that this x in here can change, either x equal to 0 and cut through straight to it, or x equal to d and go straight in here, or anywhere in between them, or even around the universe and come back to it. Which one will give me the minimum time will require that this overall distance, the difference of the whole distance, which is simply equal to AC plus CB, this distance, the derivative of this distance, I'm going to call it D, capital D, with respect to x must be equal to 0. And that's why the least time principle, so I'm using Fermat principle, is really not a minimum, but actually an extremum, because the first derivative equal to 0 does not necessarily guarantee that you will have a minimum. You have to take the second derivative to see if it's a minimum or maximum. But we don't care about that. All we care about is actually an extremum. Okay, and that's why if you look at the verbiage and the principle itself, I use the word minimum or maximum, as long as the derivative is 0. We don't care. Okay, so I'm going to take this two terms and take that derivative and require that the derivative is 0. So what I'm saying in here is that the derivative of AC with respect to x plus the derivative of CB with respect to x must be equal to 0. The derivative of AC is the derivative of inside the square root, which is 2x divided by this whole square root. In other words, you take this expression, if you take derivative of this stuff, you drop the 1/2 first, okay? And you take the derivative of the inside, which is 2x, and the 2 cancel the 1/2. And then you lower the power from 1/2 to 1/2 minus 1, which is equal to negative 1/2, which will make it into the denominator. So what we will end up with is plus is 2x over 2 square root of a squared plus x squared. And in here, we're going to do the same thing. The exception is I have a minus x in here. So this is going to be, again, b squared plus d minus x squared. And the whole thing is to the power 1/2. Again, we drop the power, and we take the derivative of the inside. And that is actually minus 2x, because d is just a constant in here. So it's minus 2x, and plus, of course, this divided by this power to the power 1/2 minus 1, so it's going to be negative 1/2. Okay, and since we have to take about the same derivative, so don't tell me to make a change of variable and take the derivative with respect to x minus d, because if you do that, then you have to change the same change in here, because we're taking the derivative with the same constant with the same variable x in here. So don't take it with respect to negative x on the other side. It's going to be an error. So the sign negative is inherent to the problem. So it's not something that is artificial. So it's minus 2x divided by 2 times the square root of d squared plus, b squared plus d minus x squared under the square root. This must be equal to 0. Cancel the 2 from both sides. And leave the x there. Don't change it. Don't cancel it. So what we have in here, we have x over square root of a squared plus x squared equals to x over square root of b squared plus d minus x, the whole thing squared. And if you look at this expression carefully, it's x, it's d minus x. Did I say that? So you have to be careful with this derivative in here. When you take the derivative in here, you're taking the derivative with respect to x, which is a negative 1, times the power lowered by 1, which is d minus x. So it's a d minus x in here, not that I wrote it earlier. So you have to be careful with this, the way we do derivatives in here. So it's a d minus x in here, okay? So you take the derivative in here, you have to be careful with it. So other than that, other than this mistake, everything else is correct. So I have x divided by that distance. I have x divided by this whole distance, and that is equal to the sine of this angle or the sine of this angle. So it's sine of theta A actually. So this is sine of theta A, and this is equal to d minus x. D minus x is this distance divided by the hypotenuse in this right angle triangle, and that is the sine of this angle or sine of theta r. So this is sine of theta r. So regardless of what happened, always, no matter what the angle of incidence, its sine is equal to that of the angle of reflection, and this can only be true if the angle of reflection is equal to the angle of reflection. So the angle of incidence is equal to the angle of reflection. So that is basically the proof using Fermat principle by taking this derivative. Okay, we can do the same thing in here for the case of refraction, and we're going to find the same relationship. It requires a little bit more work, but it's the same point. So let me go back through it in here again. I have the surface in here actually, and I have a separation between them. And I have my starting point again, and here is A for the incidence. And then my goal in here is to reach this point in here, B. So this is theta B, and this is theta A, and this is the point B. As similar to before, I'm going to call this distance B, and I'm going to call this distance A. And this distance, I'm going to take at the origin, and this point in here is the point C, whose coordinate is X, actually. In the same fashion, this whole distance in here from here to here is B, and I'm going to require that the time it takes, the only thing you have to be careful with in here is that the speed of light in here is not the same. So I'm going to take it 1 in here for simplification case, and in here it's n. So that means the speed of light in here is equal to c, whereas in here is equal to c over n, okay? That is the only thing in here. So when I'm going to measure this distance, I really, what I'm saying in here, and I forgot to mention that, is that what I should really minimize is not the time, it's not the distance, it's the time. But because light is traveling with the same speed on both sides in here, on this side, so I really could minimize just the distance, because time is equally at the distance over the speed of light. Since since the speed is the same for this case, since the speed of light is the same, then it doesn't matter. You can just minimize the distance. So that's the optical distance is the same as just minimizing the time. But in here, I have to be really careful because I have to really find this time it takes to go from A to C. So the time to go from A to C is actually this distance from A to C, which is AC, divided by the speed of light, which I'm going to take C. If it is any other value, just take C over that index of refraction, okay? So if it is NA, then it's fine, you divide by NA. And the same thing, I have to define the distance in here, the time to go from C to B as the time C to B, and take that distance CB and divide it by C over the index of refraction in here, which is a different medium B, okay? That is the only thing that is different than the first expression. Everything else is identical. The distances are the same. Again, this distance is clearly from this geometry is equal to A squared. AC is equal to A squared plus X squared under the square root. So AC is equal to the square root of A squared plus X squared. And this distance is going to be equal to CB is equal to the square root of B squared, this whole thing, plus this distance, which is D minus X squared, okay? So plugging into that expression, everything will be the same with the expression, with the except of this NA and NB. So the total time now to go from AB is actually equal to time to go from A to C plus the time to go from C to B. And that is equal to, if I divide by a fraction, I have to multiply by its reciprocal. So NA will go upstairs. So I'll have an NA times the distance AC divided the speed of light plus NB again comes out to the numerator times the distance CB divided by NB, divided by C, I'm sorry, the speed of light. So when I take the extremum now time for this one, everything will be the same with the C will cancel. That's why I didn't disregard it in the first case completely. And in this time, even if I include it, it's going to not matter. So what is going to come out is the this NA and this NB. So at the end, if I take the same derivative as before, namely that the derivative of this time with respect to X is equal to 0, this is going to give me a sine of A. So it's going to be NA sine of A, theta A, I'm sorry. And this will have a minus in it. And that minus will actually become also the same thing. So it's going to be minus NB sine of theta B, and that is equal to 0. That is the condition for the extremum, whether minimum or maximum. So that means that NA sine of theta A is equal to NB sine of theta B in the case 1n for the second medium, which is typical problem. And that's exactly how we're going to do a lot of the problems in the homework and actually in the lab and also that to make things a little bit easier. So if NA is equal to 1 and NB is equal to n, then you can say that sine of theta A is equal to n sine of theta B. So this is the entire chapter and its glory, okay? Everything that we need to cover in chapter 33, okay? So when we meet on Wednesday, again, I know at least one of you was not here when we had this discussion about the lab, okay? That the labs are, a lot of the lab was done before. So we're not going to repeat that same lab that we did in waves. So we're going to combine some of that lab with the next lab, which is on the index of refraction. And we're going to do it next Monday. So there will be no class this afternoon. I mean, no lab this afternoon, I should say. And the lab will be, and I'm going to post the instructions for the lab this afternoon. So hopefully you can get started on it this afternoon. When we meet on Wednesday, we're going to have problems from this chapter. We're going to spend a little bit more time on these problems. And then hopefully next week we're going to, I really want to slow down a little, honestly, because we have a lot of time and very little material to cover. So I'm going to delve into a lot of this detail, especially when it comes to the image formation from the next chapter. We're going to do a lot of image formation. We're going to see how the image is formed from different kinds of optical devices, okay? And try to build it geometrically, try to build it mathematically, and see the condition. And that is where that is where we go beyond what the book is, the condition for how to focus images, okay? And that requires a Taylor expansion, and which terms you keep in the Taylor expansion is going to tell you how sharp the image is. In other words, for example, when you're taking a picture with your camera, okay, and nowadays we don't have those zoom lenses, we have just cell phones, okay, that use digital, basically zooming. But if you have a camera, you would want to focus, even with the phone, by the way. When you come close from the image becomes, at some point, becomes fuzzy. When you move back, the image starts to become sharper. When you move back, the image becomes sharper, but then you lose a lot of details. So there is an ideal distance where things start to give you sharp images, and again, it will translate mathematically to a Taylor series. This stuff is probably not in the textbook, so depending on how you guys feel about it, we may delve into it. If not, then we just do more problems. At least we get this thing hammered. Make sense? Okay, very good. So unless you guys have any questions, we still have about 2 more minutes. Okay. So I will see you guys on Wednesday. Okay, see you guys.